In this video we're going to talk about derivatives as rates of change and beginning to use derivatives with motion. So derivatives help us to find the rate of change. That's really what the purpose of them is. Okay? This is what we're going to use them for, is to help us find how things are changing. So the first question is, a rectangle has a width or a length twice its height. If the height has length S, write the area. Okay, so this is S, this is 2S. So the area, of course, we'd multiply those two together, and it would be 2S squared. Now, find the instantaneous rate of change. Well, the instantaneous rate of change, this phrase right here is, all that means is slope. And of course, we've talked about the fact that slope is just code for derivative. So all we're saying here is find the derivative of area with respect to height, S. So the derivative of area with respect to S, dAds. And you know I like Leibniz notation, and I think you're going to see why here in a minute. I find it so valuable. But this is Leibniz notation, change in area with respect to side length. So the derivative of 2S squared is simply 4S. Now the next question is, what's the rate of change of A when S is 4? So now we're just evaluating our derivative, dAds, at S equals 4. This line right here just means I'm evaluating it at what point. So I plug 4 in and I get 16. Now in terms of units, and this is why I like Leibniz notation so much, I didn't provide a unit here. Let's say that the rectangle was, everything was in inches. Okay, let me put that up at the top. Okay, we're in inches. So when I say, you know, what's the area? Well, the units for area right here is inches squared. Let me just write that right next to it, inches squared. Okay. The unit for the side length on the bottom is inches. So the units we get from the Leibniz notation, it's just inches squared per inch. And the temptation always is to say, well, couldn't we just make that inches, because inches squared divided by inch is inches? I wouldn't. You know, this represents a rate of change. We're saying the area is changing 16 square inches for every inch the side length changes. I want to really quick talk about why this is important, and a big idea here, this idea that the change in area is somehow dependent on what the side length is. And I just, because I think that sometimes gets confused. So I'm going to draw two rectangles. Okay, we're going to draw a small little rectangle, and then we're going to draw a much bigger rectangle, like that. Okay. Now let's say in this first little rectangle right here, I wanted to add some area. Okay, so I just say, well, you know what? I'm just going to kind of do it in an L shape here. We're going to add maybe a little bit right there, a little bit right here. So, you know, I kind of have kept the ratio similar, but I've added some area, kind of that L shape along the side. So I've added area. You know, I've made the rectangle bigger than it was before. You know, if I can get that a little bit better, like that. Okay. Now, on the big rectangle, let's say I want to add about the same amount. Okay, so I'm just going to add kind of, you know, same thickness around the edges. Okay, like this. So again, just making my rectangle a little bit bigger. So here, you see I've added a little, this thickness around. I did the same thing here. I kept the ratio the same, but I added some thickness. I added about the same amount to each side, and yet I added a lot more area to the bigger rectangle, right? Because I just added this little black part here in the big rectangle, but here I added this whole thing. So how the area is changing is definitely dependent on what side length we're talking about, because a little rectangle adds some area. A big rectangle adds a lot more area. So that's why if suddenly I said, well, what's the rate of change when S is 10? Well, 4 times 10 is 40, because the bigger the side length, the bigger the rate of change. Similar to the last example, but I'm finding the area of a circle as a function of its circumference. Let's start by saying that area of a circle is pi r squared. Circumference of a circle is 2 pi r. I want you to notice that the derivative of area is circumference. Okay, the derivative of area is circumference, and I'll explain why in a moment. But here I say I want the area as a function of its circumference, so let me just keep working with some algebra here. Radius is equal to circumference divided by 2 pi. Okay, let me use that. So that means that area of a circle becomes pi multiplied by c over 2 pi squared, which is equal to pi multiplied by c squared over 4 pi squared. You can do a little bit of canceling with these pi's. C squared over 4 pi, I'm going to rewrite as 1 over 4 pi times c squared. The reason I'm going to do that is it's a little easier to see that it's not going to be necessary to use quotient rule, because the denominator, this 4 pi, this is just a constant. Okay, so I just kind of pulled it right out. Find the instantaneous rate of change for area. So again, we're talking derivative. So dA dc. Well, the derivative, 1 over 4 pi times 2 is 1 over 2 pi times c. Drop the power by 1. So that's my rate of change with area with respect to circumference. Find the rate of change of A when circumference is pi. Well, I plug in pi, so dA dc equals 1 over 2 pi. C, I'm evaluating, and c is equal to pi. So plug pi in, 1 over 2 pi times pi is just 1/2. And let's do this one in metric. Let's say that this was the whole problem was done in centimeters. So again, we use our Leibniz notation. Area would be centimeters squared. Circumference would be centimeters. So my units is square centimeters per centimeter. Okay, and again, let me just briefly tell you why the derivative of area is circumference. Okay, so let's put a little circle down here like that. Let's say I wanted to add a little area, or a little area. Okay, so let's say I just kind of add a little bit. Oops. Okay, pretend I'm actually going around the outside. I add a little area around the outside like this to my circle. So when you say, well, okay, the area is now changed. It was just the black portion, but now you added this outside part. How much did it change by? Well, approximately the circumference, because all you did was go once around the outside. So the change in area is approximately the circumference. Now, of course, we're doing a limit here as r gets really small, so that's why it's exactly the circumference. An ant is crawling along a ruler. The following graph measures the ant's distance from the middle of the ruler. So you see that this would be considered the 6-inch mark. This is 0 right here. So it starts off 1 inch positive in front of that. So it actually starts here at the 7-inch mark. Okay. Well, then the ant moves from the 7-inch mark forward 2 inches, so it ends up at the 9-inch mark. Okay, it did it over 3 seconds. Over 3 seconds, it moved 2 inches. So let me put a little interval notation here. When is it moving to the right? Well, from 0 to 3. I'm going to answer these first 3 questions all at once, because then you see it turns around, it starts coming back. Okay, it went back. Here's the 6-inch mark. It goes back. It ends up 2 inches behind the middle, so it ends up at 4 inches. So from time 3 to time 5, the ant is moving to the left. Then the ant stands still for 2 seconds. You can see that because its distance away is not changing. Okay, so from 5 to 7, the ant is standing still. Then again, the ant moves forward. Okay, it moves forward 3 inches. Okay, so from time 7 to time 8, the ant is moving to the right, and then it ends by moving 1 inch backwards. So from 8 to 9, the ant is moving left. Now, if you're in physics, you know the difference between displacement and distance. Displacement is how far you are from where you started. Distance is how much total amount did you move. So displacement, we started at the 7-inch mark right here. We ended at the 6-inch mark here. So the displacement is just -1 inch. That's all you did. You just moved 1 inch back. But distance, well, here we moved 2 inches forward, so 2 inches forward, plus, then we moved 5 inches backwards, so 5 inches back, then we moved 3 inches forward, so 3 forward, and then we moved 1 back, for a total distance traveled of 11 inches. Along the same lines, the velocity graph. Well, velocity is simply speed with direction. A positive velocity tells me you're moving forward, and negative velocity means you're moving backwards or to the left. So let's just look here and let's draw the velocity. So here you move 2 inches in 3 seconds. So just, about 2/3 was the 2/3 inches per second. Right about there. There's the velocity. I'm going to do velocity in blue. Let me put that. Then, here we moved 5 inches backwards. 5 inches backwards in 2 seconds. So we've got to say it's backwards. It's moving back. It's a negative velocity. So, yeah. And of course, here we didn't move at all. Right? So if you stood still, your velocity was 0. Here, you move 3 inches in 1 second, so you were going 3 inches per second. And then finally, you moved back 1 inch in 1 second. Again, it was back, so it's negative. So that's those little blue lines, that's the velocity graph. Now you'll notice that we did all of that by doing slope, because velocity is the derivative of position or displacement, the graph. Okay? Sorry for my poor writing there. Now speed is the same, measures the same thing but without direction. So let's change colors here. Let's go green. I'm going to graph speed in green, and speed is simply the absolute value of velocity. We don't use the negatives to say backward or forward. So really, just every time I see a negative, like this one would be the same, but this other one would come to positive 2.5. 0, of course, would be the same. 3 would be the same, and this one would go to positive 1. So speed is simply the absolute value, so you reflect all the negative velocities up to be positive.